What I'd like to do is to use my time to sketch some thoughts on an issue that I feel is really important in our modern age, and that is the question of how we distinguish fact from fallacy, opinion from reality, and in so doing, guide our community through to a successful and safe future. Now, this is a long conversation to be had, and 15 minutes is hardly time to do it justice. But in the limited time available, let me try to do my best to inject some ideas and thoughts through the means of an extended example. This is going to be fast and high level, but you should be able to locate all of the supporting material at leisure afterwards. So in late 2023, a rescue helicopter was dispatched to retrieve an injured hiker near the crest of an exposed ridge in the mountains of New Zealand. As the pilot decelerated towards the pickup spot, they found themselves in a steep descent from which they were unable to escape. Now, very fortunately, nobody was injured, and all the occupants and the hiker were eventually evacuated. The accident was attributed to something called the Vortex Ring State, an aerodynamic phenomenon that I've spent the better part of the last 2 decades trying to understand. Now, it's quite likely that you've heard of the VRS, but what is it exactly? Well, unfortunately, the explanation that most folk would give, in terms of descending into your own downwash, is oversimplified to the point of being wrong. The fact that this description is still being circulated in influential circles is a whole other discussion, perhaps for another time. We now know that the real explanation is a lot more interesting and physically beautiful. The rotor wake is inherently unstable, and in descending flight it can swap from its usual tubular form into a characteristic donut-shaped structure in which the rotor's ability to generate thrust is significantly curtailed. Although the flow in the mean within this donut is essentially recirculatory, one of my brightest PhD students, Gary Arlin, was able to show 20 years ago, through months and months of painstaking computational simulations, how vitally important it is to understand the detailed physical mechanisms that govern how the vortical structures evolve within the donut if we are to understand properly the flight dynamic effects of the vortex ring state. Indeed, if we acknowledge these instability mechanisms as fundamental to the vortex ring state, then we can develop a very elegant and simple model for where the region affected by the vortex ring state lies on the flight envelope. And, indeed, the predictions of this simple model agree particularly well with the body of experimental evidence which has been gathered since the dawn of rotor-borne flight, showing where a helicopter might be susceptible to the vortex ring state. So, could we use the model to explain what had happened during the accident in New Zealand? Fortunately, the aircraft had the equivalent of a black box on board, and we could use that data. This first plot, showing the variation of speed with respect to the ground, showed a curious feature, however. The catastrophic descent of the aircraft seemed to have begun well before the vortex ring state should have kicked in. Even after adding in the effects of the horizontal wind, and hence doing the right thing by expressing the data in terms of airspeed rather than ground speed, this anomaly remained. Now, pilots are often trained to avoid the vortex ring state by adopting a simple rule of thumb. The most common version of this is not to descend at greater than 500 feet per minute if traveling slower than 30 knots. The pilot in this case was in fact doing a very good job of sticking to this rule, despite his very high workload at the time. But most pilot training, and certainly the rule of thumb, doesn't account for 2 important additional effects. Firstly, deceleration and the associated backwards tilt of the rotor increases the effective rate of descent as seen by the rotor itself. Secondly, a similar effect, particularly common in mountain flying, is induced by the fact that the wind follows the local topography. Any upslope component of the wind, tending to increase the effective descent rate of the rotor, can be very difficult for the pilot to perceive, however. Accommodating these effects to the best of our abilities ended up showing that vortex ring state was practically certain as the aerodynamic cause of the accident, with the data track showing the aircraft to have entered the vortex ring state just as the descent rate started to build up. The analysis was technically acclaimed, but as usual, social media turned out to be the court of opinion, and one comment certainly stood out. A masterclass in hindsight bias and making the facts fit the theory. Well, yes, but that's also the basis of the scientific method, which is in fact a robust methodology to reach rigorous conclusions, even if they are uncomfortable and don't conform to your particular tastes. The commentator didn't seem to appreciate that the methodology admits very little wiggle room. Either the data fits the theory or the theory is wrong. So on to the next chapter in the saga. A couple of years ago, I gave a lecture at the EASA Rotorcraft Safety Symposium, showing how certain features of eVTOL physical design and proposed operational strategy might render them particularly susceptible to the Vortex Ring State. The content was particularly motivated by EASA proposals at the time to constrain the final descent of these vehicles into urban vertiports by forcing the last stages of descent to lie within a steep conical confinement extending upwards from the landing site. Now, the geometric argument was moderately complex, but it showed that the possibility of entering the vortex ring state would have to be considered in every single instance when descending into a vertiport where the dimensions were constrained in this way. The video of the presentation on YouTube got quite a lot of attention, I'm glad to say. But after about a year, this rather interesting comment appeared, which to my mind got to the heart of how a good proportion of the community probably happens to be thinking about these sorts of issues. The author of the comment appeared to be suggesting that we might be absolved from considering the risks posed by VRS at all. Some all-powerful technology would come to our rescue and allow us to circumnavigate the issue in its entirety. The point is well worth considering. Was the comment just wishful thinking, an article of faith, if you will, or a well-supported scientific statement? Well, referring back to the New Zealand accident, didn't the pilot's rule of thumb constitute a rudimentary form of envelope protection? In that case, despite their best intentions, the intervention there had proved less than effective. In the urban eVTOL context, the complexity of the winds to which the vehicle might be exposed will in many cases make mountain flying look like a walk in the national park. So in much the same way as the pilot of the ill-fated rescue helicopter, how will we know where we are on the flight envelope? The kinds of instrumentation that might help us to resolve the wind environment are coming, but at the moment are limited in capability and heinously expensive. So how might we actually construct a workable protection strategy against the vortex ring state? Firstly, the model that Gary helped develop is good, but generic. We'd need to do a lot better before hardwiring that into some flight control software, running the risk, of course, that it's all too easy to be either too conservative or alternatively excessively naive in the process. And the research quality tools that we were using to show just how important the detailed dynamics of the vorticity is to defining the properties of the VRS are generally considered to be too expensive and difficult to use in industry. I vividly remember being alarmed at a senior industrial proponent's assertion at a recent Mikulski lecture that speed of computation and ease of use could in many cases trump accuracy of prediction in the industrial context. Well, in the case of VRS, this attitude is distinctly dangerous, and industrial simulations such as this, where all semblance of structure is rejected in favor of speed of execution, risks taking us back to the days of descending into our own downwash. We need to be careful of what we believe and why. So to the final chapter, a panel discussion, perhaps quite similar to the one that we're having now, with speakers just as illustrious. During the course of the discussion, the CEO of a well-known eVTOL company adds to the discourse, again effectively to absolve the industry from paying attention to the phenomenon, and he does this by making two seemingly rather profound and authoritative observations. Firstly, that the propulsors of a multi-rotor vehicle won't all enter the VRS at the same time, the implication being that the remaining functional rotors will save the day. Well, firstly, I wouldn't be so sure. A lot of work has gone into showing that one rotor going into the VRS can have a knock-on effect in promoting VRS-like behavior on other surrounding rotors. I can imagine that this is not a feature that most manufacturers would like to explore during flight test, but wishful thinking won't make the physical arguments go away. Secondly, there are instances where all the rotors not going into the VRS at the same time is actually part of the problem. Witness the asymmetric entry into the vortex ring state that was held responsible for the crash of the Osprey so many years ago now that engendered most of the understanding of the phenomenon that we now can rely upon. All I can say is that if you're going to engage in wishful thinking, be careful what you wish for. And finally, if you're going to rely on importation of ideas from other domains, no matter how analogous they might be, make sure that your analogies are valid. So, nacelle tilt is indeed a powerful escape mechanism that twin tilt rotors can use to escape from parts of the VRS domain. But in the eVTOL case, the double-edged sword is that the algorithm used to trim the aircraft, if not designed with specific exclusions in mind, can actually precipitate the rotors into the VRS just as quickly as they can extricate them. Now, I believe it's incumbent on us as serious professionals to thrash through these issues and to debate them fully out in the open, rather than in closed chat rooms and via Facebook and LinkedIn. Remembering that it is the men and women at the sharp end who will bear the brunt in terms of the safety and reliability of the products that we develop. Indeed, it is these brave people that are left exposed by the weaknesses in our logic and by the fallibilities that are embedded in our articles of faith. And they will experience them in a much more immediate and intimate way than the shareholders and investors in the companies who are agitating for immediate solutions to some of these very thorny problems. But I'm sure I've overstayed my time, so I'll thank you for listening, leave you with this final quote, and set you some homework. It's not onerous, but it's apposite. Go watch this movie if you haven't already. And if this talk strikes a chord, perhaps send me a like. Thank you, and enjoy the rest of the workshop.